Graphing accelerated motion. We are going to take a look in this video at how these graphs right here can describe accelerated motion. And these graphs that we have that we're going to be analyzing, we got by dropping a picket fence through a photo gate. And basically that is just an object in free fall. And as you can see from our motion diagram here, that an object when it's in free fall is going to have an increasing distance in time. In other words, in each interval of time, in each delta t, the object's going to fall further and further and further. So the change in distance here, the delta d, is going to get bigger and bigger for each interval of time. Well, if that's getting bigger, then the velocities must be getting bigger, or the speeds must be getting bigger. And if the speeds are getting bigger, then the object must be accelerating. So we're going to see how these graphs show acceleration. But before we do that, let's take a look at some real acceleration with free fall. Maybe before we see the acceleration, let's go ahead and take a look at it with our graph here. So we're going to take a look at our acceleration plot of those three plots first of all here, and that is our dependent variable on this axis. And we're going to see how the acceleration is affected or behaves in time here as an object is falling. And if you can see right here, our picket fence, when it fell through, we had some experimental error here due to the way the apparatus, the photo gate, picks up the data. Of course, we know by experience that gravity doesn't vary like this. It feels quite steady. So if we do a line of best fit between these data points right here, we can get a pretty good sense of what's going on. So gravity pulls us pretty constantly. So an object in free fall is going to feel a constant pull and therefore is going to be accelerated constantly. And that's what this relationship shows, again, if we take into account the experimental error involved here. So what we find out, this is a pretty simple relationship here, is that the acceleration is constant when an object is in free fall. And that's the kind of motion that we want you to learn in this particular unit, is the motion associated with constant acceleration. One other detail, near the Earth's surface here, gravity feels pretty much the same. Everywhere you walk around, it feels the same, and that is because the pull is the same. And since the pull is the same, we end up getting a constant value for acceleration near the Earth's surface. Everything falls roughly at the same rate, or accelerates at the same rate, if we ignore drag force due to air. So this is a nice little number to memorize here. That acceleration is 9.8 meters per second every second for an object in free fall. So this is our look at the acceleration plot. Now I bet you want to see those folks actually in free fall. But before we get to them, let's go ahead and pause the video right here and do a quick sketch of your acceleration plot right here. And also note that acceleration is constant, and the acceleration due to gravity here on Earth is 9.8 meters per second. After you get that down, we'll check out those people in free fall. Yeah, that's a pretty scary ride. I think I'll pass on that one. Now that we've seen that the acceleration is constant, we can better understand what's happening with the speed in time with this graph right here. So the speed, which is our dependent variable here on the vertical axis, as you can see, if we start out at a particular point here, the speed is rising right here as the time is going on here. And how it rises for each interval of time right here, the speed rises an equal amount. And so what we say is the speed versus time plot is increasing constantly. And because it's increasing constantly, that means that the slope of this particular line is constant. And that should make a little bit of sense because the object is accelerating constantly due to gravity. Go ahead and pause at this point and copy down this graph of velocity versus time and these couple of facts, and then we'll get back and look at this slope in a little more detail. So, same graph. But now if we're looking at the graph, we want to take a look at the slope of this velocity versus time plot, since it is a constantly increasing line. Since it's a line here, we can figure out the slope. And remember that slope is rise over run. So if we take this point right here and see how much it rose all the way to this maximum point here, that would be the change in speed from this point to the last point over here. And that rise is what we call delta V, the change in speed. And then if we take the run from this point all the way over to this point, that amount from here to here with time, down here as our independent variable, that would be the change in time, or our delta T. And if we take that delta V over delta T, what we end up with here is we end up with the slope. Well, if we check that out, that slope, delta V over delta T, that's our definition for acceleration. Hey, the slope of the velocity versus time plot is the acceleration. Wow. And that should make sense because acceleration is the rate of change of velocity, how much this velocity is changing in time. That's a huge concept here, so we want to make sure that we copy these couple extra notes and this information on your existing notes right now. So here's a super important fact to memorize and to put into to create some great semantic memory of, and that is that the slope of the velocity versus time plot is acceleration. So repeat that several times yourself as you're putting that down in your notes. And now for our last of our 3-3-3 plots to analyze accelerated motion, we're going to take a look at the distance versus time plot, where distance is our dependent variable. And if we look at this graph right here, it makes a lot of sense because in each interval of time, the distance is increasing. But if I look at this carefully, and it's kind of hard to tell because this one's not accentuated a lot, but if I look here, that how much the distance is increasing is getting a little bit bigger each time. That's why this is curving up. Again, this is pretty slight, but nevertheless, you should see some curvature here. The reason it's curving, again, is because now my distance is increasing, but it's increasing at an increasing rate. In other words, if we look over here, for the same interval of time, right here, and then also right here, how much the distance is getting bigger is getting bigger. So that means that the slope of this curve right here is getting larger as time increases. So it's not just the value that's getting larger, it's the slope that's getting larger here. And that's how we can tell that the distance is increasing at an increasing rate. pause the video and copy these notes down.
I hope this isn't too graphic for you.
I'm sorry about that. I couldn't help myself. Before we move on, let's take a look at a concept called the tangent line. As you can see from our last graph there, when we had our distance versus time plot curving up like this, that's actually a curve called a parabola. And you probably will have learned about that in your algebra class, or will soon. And when we have a curve, since slopes have meaning, especially for a distance versus time plot, the slope is the speed. We'll see that in the next part of the video. Since slopes have meaning, how do we deal with a slope when we have a curve here? And so that's where the tangent line comes in. So when we have a curve right here, what we can find out is we can find out what the slope is at any particular point on the curve. So we're going to start down here in the corner, and if we start down here at the very bottom, notice that the curve hasn't started upward yet. And so if I were standing on this slope, let's say I was a snowboarder and I was standing on the slope of my snowboard right here, my snowboard would be flat. So if I extend my snowboard into a line right here, that's called the tangent line. And we can see that the tangent line right here would be flat at that point. If, however, I came up the curve, let's say over to this location, and I was on a snowboard here, I would definitely feel that it was steeper now. There was some steepness to it. And so if I could extend my snowboard outward both directions from this particular point on the curve, then I would see that this would be the particular slope of that curve at that point. And that's our definition of a tangent line right here. And that helps because now if we extend that tangent line, we could really find out a rise over a run right here and actually calculate the value of that slope at that particular point. If we go up further here, whoa, now we're getting really steep, and we could see that my snowboard would be super steep up here, and the tangent line would be very steep as well right here at this particular point. So the slope would be increasing even more. And that's not just true for parabolas, it's true for any curve. So I tried to show that by creating kind of a crazy curve here. And if we're at this point, we can see this curve that's right here. If I was standing on a snowboard going this way, that the tangent would be about like that. And if I were here, the tangent would be about like that. And likewise, if I were here, that would be about the tangent. If I were right here, I didn't draw it, but if I were right here, the tangent would be perfectly vertical. If I were right here, you could see how it would be. And if I were all the way back down here, I didn't draw that one either, but you can see that it would be flat here. So this is a pretty important concept with the tangent line, so take a moment and pause the video and do a quick sketch of your tangent line ideas here. So back to our distance versus time plot here, just a couple of things to add now that we know about the tangent line and the slope. So we can see here, I've added some tangent lines here, and we can see that our slope is getting bigger and bigger. And that should make sense right here, because if you recall, the slope of our distance versus time plot, our delta d over delta t, is our speed. And from our last graph, we saw that our speed was increasing constantly. So if our speed was increasing constantly, that would mean our slope here would be increasing constantly. And if the slope is increasing constantly, that would suggest that we would get an upward curve and a parabola just like we get. So add this little bit to your notes, and then we'll wrap things up.
Whoa!
So there we go. We have our 3 graphs right here of our free fall and accelerated motion. So we accelerate constantly, have a constantly increasing speed in time, and a distance that's increasing at an increasing rate. Scratch's parting idea. And good luck as you strive for continuous improvement.